So what is the base of this logarithm since it's not here? 10. Okay, so we're really working on, oh, not like that. We're really working on log base 10 here. So I'm going to rewrite it like that for those of us that struggle a little bit with this. So you guys pass this all the way down to Daniel. All right, so I have log base 10. So first of all, do I want to plug negatives in here? Can I calculate the log of a negative? No, we talked about with this equations. Do I want to plug in 0? Can I calculate the log of 0? No. Okay. Can I calculate the log of 1? Yes, and what does it turn out to be every time, no matter what the base is? 0. Okay, so 1, 0 is something that we have that's consistent. Okay, so we plug in 1, we get 0. I could then plug in 2. There is an answer, but is it an easy answer? Does your head automatically know what power you put on 10 to get 2? No. What's a number that would be nice to plug in here and your head would automatically know what power to put on 10 to get this number right here? Say again. 100 would work. What else? 10 would work. Okay. So we know, like, if we plug in 10, that's 10 to the first power. If we plugged in 100, then our y value would be 2 because the exponent to put on 10 to get 100 is 2. Is this okay with everybody how we establish these numbers right here? Okay? Because every time there's a new base, you're going to have to make your own chart of your parent function. Now, are we going to graph the point 100, 2? No. I'm not going to. You can. Okay? You can make your graph go all the way out to 100 and then go up to 2. I'm not going to. Now, we already said we can't plug in any negative numbers. Those aren't going to work. We can't plug in 0, so I don't have to worry about putting those in my table. Are there numbers between 0 and 1? Yeah, they exist. Okay? All right, they're in there. Half, fourth, things like this. What's a number between 0 and 1 that if you put in here, you would be able to calculate the logarithm? So we're talking fractions smaller than 1, right? Like a half. Is a half a good choice for this? Not for me. I don't know what exponent you would put on 10 to get 1/2. Abigail? 0.1? Good. Okay, so 1/10. E minor over here. Okay. All right. Okay. So 1/10. Okay. So 1/10 would work. What exponent do we put on 10 to get 1/10? -1. So I know with like 1/10, I would get -1. I'm filling this into this one so we can see some patterns, and then our chart will look a little nicer for the next one since now we kind of know what numbers to plug in. What's another fraction you could plug in and you'd be able to calculate? 1/100, right? And if I plugged in 1/100, what exponent do I put on 10 to get 1/100? -2. So 1/100 is like -2. All right, so let's start looking at, thanks, Chase. Let's start looking at what's going to work on here, some points we can actually plot. So I'm going to plot the 10, 1 point. Yeah, good. I gave you guys a 10 by 10 grid. So there's 10, 1, okay? And I'm going to plot 1, 0. Now, it's kind of hard for me to plot these fractional points, like where's 1/10? How am I going to physically be able to put that on my graph different than 1/100? But at least we can get the idea. 1/10 is real close to 0. It's not very far. And it goes down to -1. So there's some point like there. And then 1/100th goes down to -2. So even closer to that, there's something that goes down like there. Okay? What if I plugged in 1/1000? What would I get? Yeah, if I plug 1/1000 here, what power do you put on 10 to get 1/1000? The answer would be -3. So as I get closer and closer to 0, I'm just going down further and further. So what this curve looks like is something like this. But do I ever actually plug in 0? No, and I don't plug in any negatives. So what this has is just like our rational functions, it has an asymptote because it gets closer and closer to 0, but it never hits 0 because we can't actually plug 0 in. So right here, along the x-axis, or y-axis, sorry, at x equals 0, there's an asymptote. So the graphs will have something in common in the fact that they'll all generally take this shape, but will they all have the point 10, 1? No. That was because the base was 10, and that's why that number worked out well. If you change the base, 10 might not be the number you want to plug in. The only point that they'll all have is the 1, 0. So if you were going to make some notes on this first graph, all the log functions will generally be shaped in a curve like this. They'll all have this asymptote at x equals 0, because all of them have that you won't plug in 0 or negatives. And they all will have this point 1, 0, because no matter what the base is, when I do log of 1, I get 0. Okay? Everybody okay with this first one that we're looking at? So if somebody asks you to graph something like this, okay, this log is base 10. You start with a chart of these points, okay? And then you do the x is going to have plus 4, the y is going to be times by 2 and added by 1. You do all the same things we've done before. Getting the beginning chart is a little more complicated because it's a log function and because they're all different depending upon the base, okay? Question, Natalie, you have a question? So remember that the base is 10. So if we plug in, like, let's say we plug in negative 10, right? And we try to calculate log of negative 10. It's asking you 10 to what power equals negative 10, but there's no exponent that will change this to a negative. So there's no solution to that problem. So it's impossible to calculate. So the same thing happens when you put 0. There's no exponent powers that you can put on a positive number base that make it turn into 0. Okay? Mm-hmm. All right, so I want you guys to try the next few, and then we'll come back together in like 10 minutes. So the next one has a base of 2. So that's going to change some of the numbers that you would put in the chart here. Okay, one of the points we just talked about will stay the same, but the rest of them will change based on the fact that this is 2, and 10 is no longer a friendly number to plug in when I have a base of 2. The next one is a base of 3, and the one after that is a base of 1/2. Okay, so I want you guys to work with the people in your group. If you have no clue, those are your like little lifelines right now. I want you guys to try and get charts and see if you can get curves that make sense. Then we'll come back together, see what people picked, how they figured that out, and then try to use those to graph one that's like this, that has transformation. Okay? Okay. So let's look at 2. So with a base of 2, okay, what are good values to plug in? In other words, what numbers could you put here, and then you would be able to figure out the exponent to put on 2 to get that number that you plugged in for x? Abigail? Okay, so 4 would be a good number. What else? James? 1/2. What else? Abby? 2. What else? Gianna? Good. Okay, so these are all good values. So we see a little pattern here. Last time 1/10, 10, 100. This time 1/2, 2, 4, and 1 works in all of them. So I'm kind of seeing a pattern that if I have to build the parent function, I would probably start each time with the reciprocal. Grab a handout on my desk, honey. I would start each time with the reciprocal, and then 1, and then the powers of that one that I have to use, right? So when you plug in 1/2, those of you that are struggling with where we're getting these numbers, when you plug in 1/2, and I then write the wrong thing. Okay. And you're calculating log base 2 of 1/2. Remember, that's a question. To find out what y is, you have to know what exponent would you put on 2 to get 1/2. So that's how we're coming up with negative 1. Okay. So when you plug in 1, there's a 1 right here. And then that's your x value. Your y value is what exponent do I put on 2 to get 1? 0. Okay. And then this pattern continues. So if I plug in 2 right here, I'm trying to calculate this. Okay, my x was 2. It went in this spot. The y is going to be the answer to whatever this is. So what exponent would you place on 2 to get 2? 1. Okay. Then you change this to 4. So 4 is your x. You're calculating your y. What exponent do you put on 2 to get 4? 2. So we can't memorize one parent function, but we can kind of see a pattern happening that could help us build this chart quickly. We could always use the reciprocal of this, right? And then 1, and then powers of that, like 2 to the first, 2 to the second. Okay? So that will look like this on our graph. 1/2 gives us -1. 1 gives us 0. 2 gives us 1. 4 gives us 2. If we wanted to go even further, what's the next thing we could plug in? 8. Okay? So if we plug in 8, we get 3. And so then we get this curve like this. And again, I know that that will get closer and closer to the y-axis, but it won't actually cross the y-axis because I can't actually plug in 0 and get an answer. So you still have this asymptote here at x equals 0. Right? So let's just look at what each of the other ones would look like. Okay? With a power of 3. So the numbers I would plug in, I'm trying to establish this pattern in my head. Sorry, yeah, Abigail? Good. Okay. I would look here. So let's say I have a problem, but it's not like this. It's got like all these transformations. But I'm going to build this first. Then I'm going to build a new chart with the transformations. So I'll start like she said. This says 3. I'm going to start with 1/3. And then I would use 1 and then powers of 3 from there. Okay. So 3 and then 9. But remember, when you're using these as x values, they're going in here, and the y value is the answer to the logarithm. So it's the power you place on 3 to get that. So for 1/3, the reciprocal, it's -1. For 1, it's 0. For 3, it's the first power, and 9 is the second power of 3. So you're seeing these same answers show up every time. Do you notice that our y values kind of look the same every time? That's because we're specifically picking out the x's that we know will make those things that are easy for us to find and plot. Okay? So we would want to plot 1/3, -1. And just do your best with the fractions. This probably doesn't look much different than my 1/2, -1. That's okay on your paper too. So 1, 0, 3, 1, and 9, 2. So like this. And again, we have this asymptote at x equals 0. Is that all right? We see kind of the pattern here. So bummer, you can't memorize one parent function. There's infinitely many. Good news, at least to get it each time, there's kind of a pattern you can follow to come up with the parent function chart. All right, so the last one I put in had a base that is a fraction, but we can still use the same idea that we were talking about before, and we'll see how this affects it. So let's use the same theory that we came up with before and then see how it changes. So we said when you see the base, try using the reciprocal, right, which would be 2. And then we would get -1. We still want to plug in 1 and we get 0. We want to use the base itself. So 1/2. Okay, so remember, you're now calculating log base 1/2 of 1/2. So what's that going to be? What power do you put on 1/2 to get 1/2? 1. So even though these might look different than you feel, it's following the same pattern as before. Okay? What's another power of 1/2 that I could plug in? Okay, yeah, so we'll get to that one in a minute. If we followed the pattern of our other ones, we would use 1/4 here, because then we would get 2. But James is saying you can plug in 4. Do you guys get that? You can plug in 4 because even though you have this, so 2 squared would be 4, but you have 1/2 and you want to flip it over. So what is the answer to this calculation? -2. We want to square it, but we want to flip it over. So we could do other things. We could get 4, -2. Okay, so let's plug in some of these points. So 2, -1, 1, 0, 1/2, 1, 1/4, 2, 4, -2. You could plug in 8 and get -3 if you wanted. Okay, but you just got to start with some values. But this is what's happening here. And then there still is this asymptote at x equals 0. So why does it look different than the other ones? It's still the same type of curve. James? Good. The base is less than 1. Okay? So when you actually plug in higher values here, okay, you need to flip it over to get those higher values, so you're getting negative answers. So all of these could be what parent functions look like, and that's how we'll come up with the chart every time. Okay? Once we've established the chart, we want to do the same kind of stuff we were working on in our weekly review yesterday in order to graph the new function. I'm going to give you guys a minute to get this down. So let's look at this problem on the back. So the problem is log base 3, but it has transformations. It has a 1/2, it has x minus 1. But you still want to start with the parent function. So remember, the parent function is without the transformation. So for us, the parent function is this. So then we kind of made a little cheat sheet for you. You could just look back on the other page because we've already created it. But on a test, you wouldn't have that in front of you, right? So let's say that you're sitting down to a quiz, test, homework without your notes, something like that. You know you need this parent function so that you can do the transformations here and continue it. So this parent function, if I had to recreate the chart real quick, we said to try and use the reciprocal, and then like 1, and then powers of the base, like 3 and 9. Okay? If I plug 1/3 in here, what power do I put on 3 to get the 1/3? We established was -1. And then 0, 1, and 2. So this is the parent function chart. Okay? I didn't exactly memorize it because you'd have to memorize infinitely many of them, but I kind of memorized how to make it so I could make it quickly each time. Okay? So then we have to do the transformations. So looking at our function up here, are there any horizontal transformations? Is there anything up there that affects the x, the stuff inside of the logarithm? Yes, okay? There's a -1 up there, but what does that really mean in transformation terms? It moves it right 1, which on the graph means we're adding 1 to our x coordinates. So everything that we build in our x coordinate right here, where it says x, you guys could cross that out and actually write x plus 1. I'm going to be like 1 lower than you because it doesn't sit well on here. Then look at the function, and are there any vertical transformations? So is there stuff outside the logarithm, so being added or subtracted behind it or multiplied in front of it, the stuff that would affect vertical things, vertical stretches, compressions, reflections, or translations? Okay? So the 1/2 is a vertical compression. So our y values are all getting multiplied by 1/2. And then I'm going to do what we normally do to transform this function. So I'm going to take all the x values and add 1 to them. Okay? So this is going to be 1 1/3. This is going to be 2. This is going to be 4. And this is going to be 10. Then I'm going to take all my y values and multiply them by 1/2. So instead of this being -1, it'll be -1/2. 0 times 1/2 is still 0. 1 times 1/2 is 1/2. And 2 times 1/2 is 1. Okay? I'm now going to plot these new points on my graph. Okay? So 1 1/3, -1/2. 2, 0. 4, 1/2. And then 10, 1. And that looks about right. It looks like I could fill in something that's the shape I expect, right? Like one of those curves. Here's the thing. You want to put the asymptote in before you draw it, so you know where to draw the curve. Where should the asymptote go? So think about it. The asymptote used to be at 0. What's the only kind of transformation that's going to move your asymptote? If you stretch and compress it, is it going to move this guy? No. If you reflect it, it's still going to be right where it was. So the only thing that's going to move it, if you translate it up and down, it already goes completely up and down. So the only thing that's going to move that asymptote is translations left and right. Okay? So look at what you did. Did you add anything or subtract anything to your x coordinates? All the x coordinates got moved right 1. Okay? So your asymptote for this one used to be at x equals 0. You can literally, whatever happens to x, don't know why that's happening. You can just add 1. Our new asymptote will be at x equals 1. Does that make sense to everybody? Whatever you did to the x's right here, you can do that same thing to this number right here, and you'll have the new place of your asymptote. Okay, the only thing that's going to change it is when you add and subtract, because if you multiply 0 by anything, it just stays 0, and then only the addition and subtraction. So whatever you do here to all your x coordinates, you're going to do that to shift your asymptote as well. Okay? So here's my asymptote now at x equals 1. So I can kind of see how that curve, oops. Here we go, like that. Okay. So new things that are a little bit different, coming up with this part, right? And then keeping track of your asymptote along the way. Is that all right with everybody? Natalie? Uh-huh. Then you adjust the asymptote as well. You can even, if you're like, I don't understand, you could literally do anything you do to x, you can do to the x value that was your asymptote and have the new x value. Because when you multiply, it's going to times by 0. It's not going to change it. Only the adding and subtracting at the end will end up affecting it. Okay? All right, so how do we find a y-intercept? Okay, so Chase is looking at the graph and going, there isn't one. So you're right. So if you notice that and you have confidence in your graph, and I ask you about x and y-intercept with one that you've already graphed, you could say right now, no y-intercept. Let's say on the test they were separate, because some of the ones on your function test were, that you graphed some of them, and other ones you found the intercept of and you didn't have the graph. How algebraically would you have started finding the y-intercept? Okay, so we plug in 0 for x. So let's say we did this. Let's say we either didn't notice on the graph, or they gave us this problem with, and we didn't have to graph it, and we were supposed to find the x-intercept or y-intercept. So I plug in 0 for x. The first thing I'm going to simplify is all this stuff in the parentheses that's inside the logarithm. The next thing you would want to do is calculate this and then times it by 1/2. But what is log base 3 of -1? Impossible. Remember how we talked about checking our log equation answers, and if it's 0 or negative, it can't be done? So if the thing I'm trying to find is undefined, then it doesn't exist. If the calculation is undefined, then it doesn't exist, okay? So this is undefined. So that means I have no y-intercept. So again, if you have the graph and you know your graph is right, and I ask you, and you just wrote no y-intercept right away, totally good. If you don't have the graph, this is the sign algebraically that you would be like, oh, this doesn't work. There must not be one for that graph. Okay? All right, how do I find an x-intercept? Plug in 0. And so you guys kind of, yeah, so again, this graph was really nice as far as intercepts go. You could see there was no y one, and you can see exactly where the x one is. So if it's on the graph, I can go to the graph and say, I already know, it's at 2, 0. But if I ask you without it, or if it doesn't graph so nicely, what are the algebraic ways that we find the x-intercept? Plug in 0 for y, so then our equation looks like this. Now this looks a lot like what we were doing last week, right? This is why we did that stuff, so when we got here, we wouldn't have to relearn this, so we reviewed it ahead of time. To solve this, we first have to get rid of anything that's not part of the logarithm, so like the 1/2. So I'm going to multiply both sides of this equation by 2. So 2 times 0 is 0, and 2 times 1/2 will be 1. And then how do we solve a log equation when we only have one logarithm, and we need to get x out of the log? What did we say to do? Exponential form. So what's our base? 3. And what's the exponent to put on that base? 0. And then that will equal x minus 1. Okay? What is 3 to the 0 power? 1. So if it's something like this on the test, yes, you should be able to calculate that 3 to the 0 power is 1, or 3 to the first, or 3 to the second, 3 to the third, 3 to the fourth. After that, you could just leave it in the exponent form if you wanted, okay? So I have this. And then I would add 1 to get x completely alone. So I would end up with x is equal to 2. And remember, the way that we write my x-intercept then is it's the point 2, 0. Again, if it's on the graph and I'm asking you about a graph, I have no problem with you using the fact that you're intelligent enough to look at the graph and figure it out, that you don't need to do that. But if you're being asked independent of a graph, like to find the intercepts without looking at the graph, make sure you understand algebraically how to do it as well. Or if this doesn't cross at like a nice point, you'll have to do it algebraically to get the exact value. Okay? Any questions about this one? Okay, so one more. So log base 1/2. So again, you would go through a bunch of stuff to find the parent function. We already found this parent function. So you could, I don't know why it's not writing in the right spot. Okay. So you guys could go and look on the other side for right now, because we just figured this out about what the parent function is. So for 1/2, we said it's good to use 1/2. Okay. Got 1. We used the reciprocal of it. 2 gave us -1. We used 1 and we got 0. And then if you guys wanted some more points, we established that we got this 1/4 2, but that might be hard to plot. So we kind of talked about you might want to get 4 -2. So these are all points that we came up with before. So I might not want to use this one. I might not need it. Okay, a couple points around this is good enough. So in my chart, when I look at this, there's nothing happening to the x values. See how the x is in the logarithm, but nothing else is in the logarithm with it? This +4 is after the logarithm because it's not in parentheses with the x. Okay? That means all the x's are going to stay exactly the same. There's nothing multiplying them or shifting them left or right. Okay? That also means that our asymptote that was at x = 0, since there's nothing happening to x and no transformations, is going to stay at x = 0. And so I'm still going to use the 1/2, the 1, the 2, and the 4. But the y values are going to get changed. What's going to happen to the y values according to the transformations that show up here in our equation? They're going to multiply by -2 and then add by 4. So remember, the vertical stuff, the y value stuff, is kind of like what you see is what you get. The horizontal stuff is all a little bit tricky. So I'm going to multiply each of the y values by -2 and then add 4. Okay? So right here, 1 is the first y value. 1 times -2 would be -2. If I add 4 to that, I get 2. 0. 0 times -2 is still 0. If I add 4 to that, I get 4. -1. -1 times -2 would be +2, and when I add 4 to that, I get 6. And then -2. -2 times -2 is +4, and when I add 4 to that, I get 8. So I'm going to plot these things. My asymptote is still at x = 0. I have 1/2, 2. I have 1, 4. I have 2, 6. Mine's up there. And then I'm kind of running out of space just because of the way my graph is. But then you would have 4, 8. So the graph is going like that. Okay? It's curving around like this. Why doesn't it look like the 1/2 one that we saw before? Why isn't the curve going the wrong direction compared to the other ones? Like, flip your paper back over. Look at the 4 that we did at the beginning today. See how the first 3 all went the same, and then the 1/2 was supposed to go the other direction, right? It was like supposed to, the flat part of the curve was supposed to be at the bottom, not at the top. Why now is it at the top? Kat? Good. We're multiplying y by a negative, so it's causing that whole vertical reflection thing where we flipped it over the x-axis. So it actually makes sense. It's okay that it's like this, right? Okay, so Y-intercept. Do we expect a Y-intercept? Look at your graph. No. Okay. And again, we would see that when we went to do the calculation. Yeah, maybe. Because when we plug in 0 for x, this is what we would be calculating. So you would want to do this first right here. How do you calculate log of 0? You don't, right? Remember, it's impossible for us to figure out a power that changes things to 0 or a negative. So this, again, is undefined. That's why there is no y-intercept. And again, you can see that up on the graph. For our x-intercept, do we expect an x-intercept? Yes. Is it nice like last time? Can we see exactly where it's crossing according to our points? No. Okay. So we're going to have to use some algebra to help us figure it out. Yeah, I know. I'm just hoping it will come back, see? Okay, so just like last time, you need to isolate the log first, and then we'll be able to solve for it. So we want to subtract 4 and then divide by -2. We want the logarithm alone. Okay, so when we subtract 4 from each side, it will look like this. And then we would divide by -2. So we get 2 equals log base 1/2 of x. So again, you're at this point where you need to solve for x, and it's stuck inside of a logarithm, so you should change it to exponent form. Okay? So this changed to exponent form. The base is 1/2. The exponent is 2, and that will equal x. Okay? So x is going to be equal to 1/4. So our x-intercept is going to be at 1/4, 0. Yeah, Sophia?
So basically, when there's going to be a y-intercept, isn't this x minus, not with plus 2?
It's got to get shifted to the left for us to get an x-intercept. Good. Or a y-intercept. Thank you. Okay. Is this all right with everybody? Okay, so homework tonight. There's 7 problems, but I'll be perfectly honest with you. Here's what we have going. Tomorrow, we're going to do the same thing for exponential functions. Okay? And then you have 7 or 8 problems to graph of those and find their x and y intercepts. I'm not going to check it until Thursday after you take your quiz. Your quiz will be really short, your weekly review quiz. Okay, it'll be like 1 graphing problem from the weekly review. Okay, so study your quadratic, square root. That won't hurt you because we're doing the same thing here. And then after that on Thursday, we're going to stamp these 2 homeworks and we're going to spend time going over the answer. Friday, some of you will be reviewing and some of you will be retaking. You get a 3-day weekend, okay? Then Tuesday, Wednesday next week, we're going to be working on review of this, and then you're going to test on Wednesday of next week, okay? The lessons are today and tomorrow. That's it. How to graph these and how to graph exponents. And then you have a week of basically practicing or catching up on whatever before you test. Taking the test Thursday of next week will allow us time for a retake if needed during your final period. You could take the final and take a retake if you need to. Okay? Does that make sense to everybody? Yes? So homework 4 is tonight's homework. It'll be posted on Canvas. I'm not going to check it till Thursday, but you're going to get another one tomorrow night. That's what I'm telling you. So if tonight's really crowded and tomorrow you have nothing, great.